Hi boys and girls. This video comprises the lecture for section 10.5 on page 739. It's actually entitled, area and arc length in polar coordinates, but we have a truncated title because I found out that arc length in polar coordinates is not an AP topic. Area in polar coordinates is. So we're going to do this part of section 10.5, but we won't be discussing arc length. Now just to clarify, arc length is required for rectangular functions and parametric functions, which we have learned and practiced doing, but it's not required for polar coordinates. So when you're memorizing your formulas, memorize the one for just your rectangular equations and parametrics, and you'll be good to go. So what is area of a polar region? Well, it shouldn't be surprising to you that now that we're graphing polar curves, that because we're taking a calculus class, we may want to be able to find the area that is generated by a polar curve. It is going to be slightly different though. Let's look at this little diagram down here. Notice that this is some section of a polar curve, supposedly, and the area that we're going to evaluate here is not from the curve to the x-axis. It's between two radial lines, because remember we're in polar coordinates now. Some radial line alpha, some radial line beta. So notice that the section isn't so much something that we would try to approximate using rectangles. Instead, we're going to approximate it using sectors, all coming from that pole or that one spot, and radial lines out to the polar curve. So it's a good idea for us to remember that the area of a sector of a circle is A equals 1/2 theta r squared. And then we're going to use the integral to add up an infinite number of sectors. So just to summarize what we're going to do here, the development of a formula for the area of a polar region parallels that for the area of a region on the rectangular coordinate system, but uses sectors of a circle instead of rectangles as the basic element of area. So now instead of looking at a curve and deciding that we're going to approximate its area by using rectangles, we're going to look at a curve as a circular region, and we'll use sectors to approximate the area rather than rectangles. And that kind of makes sense when you think about it. Since we're on polar coordinates, we're using angle measure from the polar axis and radial distance from the pole. So let's see how this works when we take an integral. Example 1, actually let's go ahead and introduce the theorem. Theorem 10.13, area and polar coordinates. If f is continuous and non-negative on the interval alpha beta, and the difference of alpha and beta is between 0 and 2 pi, then the area of the region bounded by the graph of f of theta, some function in terms of theta, between the radial lines theta equals alpha and theta equals beta, is given by 1/2 endpoints of integration alpha to beta, our function value squared, which is the radius squared, and of course the radius will be the function that is given to us. So once again, recognize that our endpoints of integration used to be points on the x-axis, maybe say from 0 to 3, or if we were integrating with respect to the y-axis, maybe from 0 to 2 or something like that. But now we're looking at a region between radial curves, and so it's as that region is being developed between one radial curve to the next, that region and the area of it is bounded by those two radial lines, which means that they will be the endpoints of integration. So on page 740, example 1, we have the rose curve here, and we're asked to find the area of one petal of the rose curve. Now you might be thinking, gosh, if I change this to a rectangular equation, I could probably do the top curve minus the bottom curve as you always have and find the area. And yes, Yes, indeed, that is true. But that's not what we're going to do today. We're going to recognize, and we've seen how these rose curves work. They're sketched out sort of in this sort of pattern. And so one rose petal, one of them, as you can see, lies between the radial lines negative pi over 6 and pi over 6. We could also do these two radial lines, pi over 2, and not sure what that line is, or this one, perhaps. I think this is 5 pi over 3 maybe, or 7 pi over 6, and then pi over 2. But any of those endpoints, as you can see, this is the same area, will work for our endpoints of integration. So we're just going to use negative pi over 6 to pi over 6. And we set up our integral this way. Negative pi over 6, pi over 6, 1/2 on the outside, don't forget that part. Our function, which is 3 cosine 3 theta d theta, and don't forget to square the function. Now this is the integral that's going to calculate the area. So let's square this function, just rewrite it. 1/2 from negative pi over 6 to pi over 6, and when we do square it, we get 9 cosine squared 3 theta d theta. Now you might be looking at this and going, I remember an identity that will help me with this. Well, that's a good thing because you're definitely going to need it. Let's go ahead and put the 9 outside and get 9/2. And I'll just put the endpoints of integration back a little bit later. And let's change this now to 1 plus cosine 6 theta over 2. That was the identity that we were using back in chapter 8-ish. And then let's keep integrating. We are going to change this to 9/2. I'll separate it now to two integrals. Let me make this 9/4 and factor out the 2 in the denominator. 9/4 and then the integral of 1 d theta, and then plus 9/4 the integral of cosine 6 theta d theta. I'll need a 6 here and a 1/6 on the outside to make everything right. And so my integral will be 9/4 theta. And then this becomes, I think, 3/8 sine 6 theta. And that's going to be now from negative pi over 6 to pi over 6. Okay, let's plug in our endpoints of integration. I'll probably have to make 2 layers here. We're going to have 9/4 times pi over 6 plus 3/8 sine of, since pi over 6 times 6 is pi. Okay, that's the first part. And then minus, we're going to put negative pi over 6 in for theta, 9/4 times negative pi over 6, then plus 3/8 times sine of negative pi over, well actually negative pi, since negative pi over 6 times 6 is negative pi. Now these two terms go away because sine of pi and sine of negative pi are 0. And so now we're going to take our remaining little bits here, which is, I believe this becomes 3/8 pi. I'll go up here and finish. 3/8 pi. Then minus a negative will give me plus another 3/8 pi, which becomes 3/4 pi. The answer. That was fun, wasn't it? Now, what makes this a little bit tedious, boys and girls, is a lot of trigs involved. And we are not fans of trig. I know this. But it's not bad to practice, and even though it's very possible that a question on the AP exam that is involving polar coordinates would be a calculator question, we would still need to be willing and ready to do it manually if necessary. You know that if you did have to do it manually, it's not going to be a terribly complicated integral as they might give you if it were on the calculator section. But don't shy away from at least knowing how to do this just in case you need to. All right, now on the next slide, it's going to be a little bit of a surprise because I already have it all worked out. When I was practicing this lecture, it took me so long to do this. I thought this video will be like an hour if I work out all of these problems because there's so much work to be done. but I would like to point out to you just a couple of things along the way, and you can certainly pause this and look at the work and admire it and ooh and ah and just be amazed later. But right now, this is example 2 on page 740. We're finding the area bounded by a single curve. Now this is a single curve, believe it or not, but it is one of those ones that intersects itself, and so it's got this little loop in the middle, and that's perfectly fine. But what we're going to do is we're going to kind of be fancy and figure out what the area is outside the little loop, but inside the bigger loop. Since this curve is being sketched out by one function, we're going to have to figure out when on the pi situation, we had the smaller loop happening and the larger loop happening. We're going to be finding basically the area of the whole thing, the small thing, and subtracting them to get the leftover pink area. So that's what we're going to do. Now let's talk about these radial lines for a moment. You can see that the small curve is being traced out. If you look at this radial line here, we're here at 0 at pi over 6, and then we're back here at 0 at 5 pi over 6. So this little curve between pi over 6 and 5 pi over 6 had its moment, okay? And so notice that what I have over here is I'm just going to find the area of the small loop right now. And that's what this whole page is, believe it or not. So we have 1/2 from pi over 6 to 5 pi over 6, because that's when all of this was happening. We've got the function 1 minus 2 sine theta squared d theta. I expanded that, FOILed it out, and I distributed the 1/2 to all of these terms, which resulted in this. Had to use the identity on sine squared, right? Did some integrating, separated this into 2 integrals, compensated. This had to end up being a 2 here, 1/2 on the outside. These were my terms. I combine like terms, and at this point I have my integral. So I add back my endpoints of integration. Plug in 5/6, plug in pi over 6, and then I said, hey, look over here. Look at all this information. See the triangle? It turns out that pi over 3 is 60 degrees, pi over 6 is 30. So when I set up this triangle, instead of putting 60 and 30, I put pi over 3 and pi over 6. And remember, opposite the 30-degree angle is 1, the hypotenuse is 2, and then square root of 3 is opposite the 60-degree angle. So as I am calculating these things, cosine of, I also said 5 pi over 6 is the pi over 6 reference angle. 5 pi over 3 is the pi over 3 reference angle. These are in the first quadrant. 5 pi over 6 is in the second quadrant. 5 pi over 3 is in the third quadrant. So we do need to know, like, sine and cosine are negative here. Sine is positive in the second quadrant, but negative for cosine, and of course both positive in the first quadrant. With all of this information at your disposal, I was able to find all of these values. 5 pi over 6, remember, is pi over 6, and the cosine of pi over 6 is square root of 3 over 2, but in the second quadrant, that is negative. That's how I did it. And then let's go down here just for a fun one. Like 2 times pi over 6 is pi over 3, right? We just need the sine of pi over 3. Sine of pi over 3, opposite over hypotenuse, square root of 3 over 2, right? Do all of this, calculate, simplify, blah, blah. This is the area of the smaller loop. Now listen, that's not the answer. That was just the area of the smaller loop. Remember that, so we found this area. What we need to do now, however, is realize that since the function is the same, the integrand would be the same for the rest of the loop as well. From 5 pi over 6 around to 13 pi over 6, which is just another way to write pi over 6, you would get the outer loop. So take this same integrand and just change the endpoints of integration. 5 pi over 6 to 13 pi over 6. Plug all those numbers in, get that area. Then once you have that area, subtract this area, and then you would have the pink region. Now, as I said, imagine me working out that whole problem. It took me like 4 minutes, 5 minutes to explain it. So if you want to look at it in more detail, look on page 740 in your book, and it's just all there in its glory. All right, the last little thing we need to talk about here is, what if we have intersecting polar curves? Remember when we had things like this in the rectangular coordinates, maybe we had something like this, and I don't know, something like this, and we had to find perhaps the area between the two. We had to subtract and find where they're intersecting, etc. Well, of course, that can happen with polar curves too. We have the circle here. There it is, the black. We have the cardioid, which is the light gray shape here. And it says find the area of the region lying between the, oops, that's not supposed to be there. That's not what it's supposed to say. Okay, let's get rid of that. And what it should say is, just to let you know as I'm looking in my book, it says find the area of the region common to the two regions bounded by the following curves. Well, let's think about the region that is common to the two. Here's the big circle, the two curves, the big circle and the cardioid. What is common is, I'll do it down here, is this little section down here, right? And the top part as well. That is the intersection of those two curves. That is the area that we're supposed to find. Now there's one small problem. You can see that this part of the region that's in gray is formed by the circle from the radial lines pi over 2 to 2 pi over 3. Then there's a point of intersection between the circle and the cardioid, and the rest of the region is formed by the cardioid from 2 pi over 3 to pi. So we actually have to set up two integrals. This is what it's going to look like. We're going to have, of course, 1/2 on the outside. We're going to have pi over 2 to 2 pi over 3, and then the circle is the radius of the that first little region. So we put -6 cosine theta d theta, and then we're going to add to that the integral from 2 pi over 3 to pi of the cardioid, which is 2 minus 2 cosine theta d theta. And it's that simple, boys and girls. Oops, I forgot the 1/2 here. Now, of course, and I forgot to square it in both cases. Oh, that's so very sad. But other than that, this is how we do it. Now, I was just about to say we have to square this, but since I hadn't written the exponent, it wasn't going to make sense. Let me get a darker color for finishing this off. We're going to have 1/2, and the endpoints of integration, pi over 2 to 2 pi over 3. I'm just going to write this now as 36 cosine squared theta d theta. And then over here, we've got 1/2, 2 pi over 3 to pi. If I FOIL this out, it's going to be 4 minus 8 cosine theta plus 4 cosine squared theta d theta. Okay, all of that d theta. Now, you can see that as I put the 36 on the outside, this is going to be 18, the integral of cosine squared theta. We're going to use our handy little identity there. And then for this one, let's factor out a 4, and that'll make plus 4, 4 times 1/2 is 2, and then we'll have the integral of d theta, plus we'll have 2, the integral of -2 cosine theta, hope I'm doing that right, d theta, and then we're going to have plus 2, the integral of, kind of running out of room here, cosine squared d theta. Now remember that with the cosine squareds you have to use the identity, and you would keep going and it would all be good. Eventually you would end up with 5 pi over 2. Now I want to show you that since we integrated from 0 to pi with these two integrals, we got half of the region. But since it is symmetric, then we can just double this to get the whole region, of which the area is 5 pi. Again, this example is on page 742, and if you want to look at it in more detail, please feel free. But as you can see, lots of trig functions, lots of using those sweet little identities that we discovered back in chapter 8. And here's your homework page. The graphic really has nothing to do with math or polar curves, but it was just appealing to me in the moment, so I went ahead and put it up here. This is your homework assignment, and this is due on Thursday, March 29th.